Our own cosmic backyard holds secrets far stranger than fiction. Just beyond the Milky Way drifts a ghostly satellite galaxy known as the Large Magellanic Cloud. This neighboring galaxy is not a placid collection of stars. It is a cosmic menagerie of bizarre and unexplained phenomena, a place where the normal rules of physics seem to break down. By the end of this journey, you will have explored 30 of its most shocking wonders, from runaway stars to missing stellar corpses. We will investigate a supernova that left behind a phantom heart and a nebula birthing stars at a ferocious, impossible rate. What single cosmic mystery do you believe could rewrite our understanding of the universe? A cosmic nursery rages with such violence that it can be seen with the naked eye from Earth, a hazy patch of light belying the chaos within. This is the Tarantula Nebula, and it is not merely a cloud of gas. It is the single most intense star-forming furnace in our entire local group of galaxies, a sprawling collection that includes our own Milky Way and Andromeda. Inside its glowing filaments, stars are born at a rate so ferocious it defies everything we thought we knew about stellar nurseries. We expect stars to form in quiet, dense pockets of gas, a slow and measured process. But the tarantula is different. It is a runaway factory, forging colossal stars, some hundreds of times the mass of our Sun, in an unrelenting torrent. These are not the gentle births of sun-like stars. This is a violent, explosive genesis. The nebula is shredded by the intense radiation and powerful stellar winds from the very stars it creates, a self-destructive cycle of creation and demolition. How can such a chaotic environment sustain such prolific star birth? Our best models of cosmic nurseries struggle to explain the sheer efficiency and power of this region. It is as if the fundamental rules of star formation have been rewritten here, in a neighboring galaxy, challenging our most fundamental assumptions about how the universe builds its largest and brightest suns. Yet the violent creation of stars inevitably leads to their spectacular demise. In February 1987, a star within the Large Magellanic Cloud ended its life in a cataclysm so brilliant it was visible to the naked eye in the southern sky. This was supernova 1987A, the closest and brightest supernova witnessed in nearly 4 centuries. For astronomers, it was a front-row seat to the death of a star, a cosmic event that should have left behind an incredibly dense, city-sized core known as a neutron star. But when they looked, they found nothing. The heart of the explosion was empty. The expected neutron star, the collapsed remnant of the star's core, was simply gone. In its place, astronomers found a bizarre and beautiful structure, a set of 3 glowing rings of gas arranged in a perfect hourglass shape around the expanding blast wave. How these rings formed remains one of the great puzzles of modern astrophysics. They are like cosmic smoke rings, relics from a time long before the star exploded. The central mystery, however, is the phantom heart. The Titanic explosion should have crushed the star's core into a neutron star, an object so dense a single teaspoon would weigh 1 billion tons. Our telescopes have scanned the debris for decades, searching for the faint pulse of a spinning neutron star or the telltale glow of its heat. We have found only a hot blob of radioactive debris, a cloud of material that hides the truth. Did the collapse form a neutron star that is somehow obscured, hidden behind this thick veil? Or did the core collapse even further, vanishing into a black hole so young and quiet that it eludes our detection? The ghost of supernova 1987 continues to challenge our understanding of stellar death, a silent reminder that even our most celebrated cosmic events can hold their deepest secrets close. That phantom heart is not the only dark secret hiding in the cloud. There is a place where light itself is devoured in a violent, ongoing feast. This is the system known as LMC-X3, a cosmic dance between a star and an invisible predator. Here, a stellar mass black hole, the corpse of a once massive star, is locked in a tight orbit with a normal, living star. The black hole's immense gravity is relentlessly pulling gas away from its companion, a process that does not happen gently. This stolen material does not fall directly into the abyss. Instead, it spirals inward, forming a superheated, whirling disk of gas known as an accretion disk. The friction within this disk is so intense that it heats the gas to millions of degrees, causing it to glow with a fierce torrent of X-ray energy, a beacon of cosmic violence. This makes LMC X3 a brilliant and persistent source in the X-ray sky, a constant feeding frenzy we can observe from across the interstellar gulf. But this system is far from ordinary. The black hole here is unusually massive for its kind, and the accretion disk itself behaves in strange ways. It flickers and changes in brightness, suggesting instabilities in the flow of matter as it crosses the point of no return. Studying this chaotic dinner table gives us a front row seat to the fundamental physics of black holes. We can observe how they interact with their environment, how they consume matter, and how they release unimaginable amounts of energy in the process. LMC X3 is not just a spectacle of destruction, it is a unique laboratory testing our theories about how these dark engines shape the space around them, one stolen mouthful of starlight at a time. Not all stellar deaths leave a silent void. Some leave behind a ghost, a luminous and chaotic echo of the explosion. Scattered across the remnants of a supernova known as LMC N49 lies a glowing, tangled web of gas and dust. This is the wreckage of a star that died long ago, but its corpse is anything but peaceful. The filaments of this nebula are not just gently glowing. They are crackling with an invisible, phenomenal power. This supernova remnant possesses one of the most intense magnetic fields ever detected in such an object. To understand the sheer force at play, picture a simple refrigerator magnet. The magnetic field within LMC N49 is quadrillions of times stronger, a cosmic force field of unimaginable intensity. This incredible power twists the nebula's structure, sculpting the expanding gas into intricate, knotted ropes and fierce shock waves that glow with frenetic energy. But what could be generating such a phenomenal magnetic field long after the initial explosion has faded? The leading theory points to a deeply buried secret, the hidden heart of the dead star. Astronomers suspect that at the very center of this chaotic glow lies a special kind of neutron star known as a magnetar. A magnetar is a neutron star born spinning at an incredible rate, and with a magnetic field so powerful it could erase the data on every credit card on Earth from halfway across the galaxy. It is a cosmic powerhouse, and its immense magnetic energy continues to pour out, energizing the entire nebula and preventing it from fading quietly into the darkness of space. This ghostly glow is not just a remnant of a past explosion, it is a live wire, a continuous broadcast from a hidden, spinning engine of almost incomprehensible power, showing us that a star's death can create monsters far stranger than a simple black hole. Deep within another vast cloud of gas known as N44, a perfect cosmic bubble floats in the darkness. This is N44F, a cavity so spherical and immense it appears to have been carved by a divine hand. At first glance, it seems like a simple story, a bubble blown by the fierce winds from a single, massive, central star, but peer inside its glowing shell and the simplicity shatters. The interior is not empty and calm. It is a forest of strange formations, dark pillars, and glowing knots of gas that point directly back toward the bubble's heart. They look like skeletal fingers or a crowd of comets, all aligned as if fleeing from the central star. This is not the signature of a gentle, steady wind. It tells a story of violence and chaos, These structures, known as cometary knots, are formed when a blast of intense radiation and shock waves from the star slams into denser, colder pockets of gas that were already present. The denser material is sculpted and eroded, leaving a luminous head and a long, trailing tail, all pointing away from the source of the destructive energy. The presence of these intricate shapes reveals that the history of this beautiful bubble is far more complex than a single star slowly puffing away. It suggests episodic outbursts, a series of violent eruptions that have repeatedly battered the surrounding cloud. This beautiful sphere is not a peaceful haven. It is a fossil record of stellar fury, a snapshot of a relentless and destructive force that continues to shape its own celestial environment. That relentless stellar fury can sometimes forge not just glowing bubbles, but celestial cannonballs. Cutting a solitary path through the vastness of the cloud is a star named HD 268835, but it is better known as a runaway. This is no ordinary star. It is a massive, brilliant blue giant, and it is moving at a staggering speed, rocketing through the interstellar medium at hundreds of thousands of kilometers per hour. A star of this mass and velocity was not born in isolation. It almost certainly began its life within the crowded, violent core of a dense star cluster, a celestial metropolis where stellar behemoths gravitate toward the center. In such a dense environment, gravitational encounters are chaotic and extreme. The leading theory for its incredible speed is a cosmic slingshot effect. Picture a binary system, two stars orbiting one another, venturing too close to a supermassive black hole or perhaps a particularly dense knot of stars. The complex gravitational dance that followed would have ripped the binary apart, with one star being captured while the other, HD 268835, was violently flung away at an astonishing velocity, ejected from its birthplace forever. The star now travels alone, a cosmic castaway on an endless journey, but its solitude is not a quiet one. As this stellar fugitive hurtles through space, it does not move through a perfect vacuum. It plows through the thin, scattered gas that floats between the stars. The star emits a powerful wind of its own particles, and this wind slams directly into the ambient interstellar gas. The effect is like a speedboat cutting across a still lake. Just as the boat pushes water into a cresting wave ahead of its bow, the star creates a brilliant, arcing wall of compressed and heated gas known as a bow shock. This glowing crescent races ahead of the star, a permanent announcement of its passage. It is a sonic boom written in light, a visible testament to the incredible forces that can launch a star across a galaxy. This runaway is more than just a speedy star. It is a tracer of past cosmic violence, its bow shock a glowing scar that marks the path of a gravitational catastrophe that occurred eons ago. Even as we map the brilliant runaways and glowing nebulae, some of the most powerful signals from the cloud remain utterly anonymous, deep within the gamma-ray sky, where light carries the energy of unimaginable cosmic violence. The Large Magellanic Cloud holds a persistent and unidentified beacon. This is not the gentle glow of starlight or the predictable pulse of a known pulsar. It is a source of raw, high-energy gamma radiation detected by instruments like the Fermi Large Area Telescope, and it has no clear counterpart. Look through an optical telescope at its coordinates, and you see nothing out of the ordinary. Point a radio dish in its direction, and you hear only silence. Yet in the gamma-ray spectrum, it shines with an intensity that demands an explanation. What cosmic engine could possibly produce such phenomenal power while remaining completely invisible in every other wavelength? The leading theory points to a hidden stellar corpse, a pulsar we simply cannot see. Pulsars are rapidly spinning neutron stars that sweep the universe with beams of radiation like a cosmic lighthouse. If one of its powerful beams were pointed away from Earth, we would never see its telltale pulse in radio waves or X-rays, yet the surrounding region of space, a cloud of particles called a pulsar wind nebula, could still be slammed by the pulsar's fierce energy, causing it to glow brightly in gamma rays. It would be like seeing the brilliant glare of a lighthouse lamp reflecting off the fog, while the lighthouse itself remains hidden behind a wall, its rotating beam forever pointed away from us. But there is another, far more exotic possibility. This mysterious glow could be a signature of something we have never directly seen: dark matter. Theorists suggest that if dark matter particles are their own antimatter counterparts, they could annihilate upon contact, converting their entire mass into a flash of pure energy, including gamma rays. A dense concentration of dark matter within the cloud could be the site of a continuous, silent annihilation, a ghostly fireworks display that we perceive only as this unexplained, steady source of light. This unidentified object represents a fundamental limit of our knowledge. It is a stark reminder that the most powerful phenomena in the universe can still hide in plain sight, their true nature masked by the very energy they release. This chemical imbalance points to a deeper mystery within the cloud's stellar population. The Large Magellanic Cloud is strangely rich in a specific type of aging star known as carbon stars. These are not like our Sun. In their final stages of life, these stars become chemical factories, and in the case of carbon stars, their internal processes have flooded their atmospheres with so much carbon that it forms a sooty haze. The carbon molecules in their outer layers absorb blue light, making these stars glow with a deep, distinctive red color. They are cosmic embers smoking in the darkness. What is truly puzzling is not their existence, but their overwhelming abundance. The Large Magellanic Cloud contains a far higher number of these carbon stars per unit of mass than our own Milky Way. This is a direct challenge to our models of how stars live and die. The evolution of a star is dictated by its initial mass and, critically, its initial chemical composition. Stars in the Large Magellanic Cloud are, on average, what astronomers call metal poor. This does not mean they lack iron and nickel, but rather that they contain lower amounts of all elements heavier than hydrogen and helium compared to stars in our own galactic neighborhood. This difference in starting material seems to be the key. In a metal-poor environment, the internal machinery of an aging star operates differently. The balance of nuclear fusion and the way a star dredges up newly forged elements from its core to its surface are altered. It appears that in the Large Magellanic Cloud, the conditions are just right for a much wider range of stars to successfully become these sooty, carbon-rich giants. It is as if the galaxy itself has a different recipe for stellar old age. This population of crimson stars is more than a collection of pretty lights. It is a fossil record telling us that the history of element building, the very ingredients for planets and life, has followed a different path in our neighboring galaxy. Why does a slight change in a galaxy's initial chemical recipe lead to such a dramatic difference in its stellar retirees? The answer forces us to refine our understanding of stellar life cycles on a cosmic scale. This chemical imbalance in its stars is mirrored by the very structure of the galaxy itself, where vast regions of nothingness are actively carved from the cosmos. Drifting within the cloud is a colossal cavity known as DEM L106, a superbubble so immense it could swallow entire star systems. This is not a simple void. It is a testament to collective stellar power, a cosmic clearing forged by the combined fury of dozens of massive stars. For millions of years, these stellar giants have bombarded their surroundings with powerful winds, streams of charged particles moving at supersonic speeds. Then, one by one, the most massive of these stars reached the end of their lives and exploded as supernova. Each detonation delivered a titanic shockwave into the surrounding gas, pushing it outward and inflating this single, gargantuan bubble. The energy required to create such a structure is almost beyond comprehension, the cumulative output of an entire stellar generation, but the story of DEM L106 is not just one of destruction. Look closely at the edges of this great emptiness, and you witness a cycle of rebirth. The expanding shell of the superbubble is not a smooth wall, it is a tangled, chaotic web of glowing filaments and dark, dense knots of gas. As the shockwave from the bubble's expansion plows into the surrounding interstellar medium, it compresses the gas, squeezing it with immense force. In this cosmic pressure cooker, gravity gains the upper hand. These compressed knots collapse under their own weight, triggering the birth of a new generation of stars. This process, known as triggered star formation, turns the superbubble into a self-perpetuating ecosystem. The death of old stars directly catalyzes the birth of new ones on the very surface of the cavity they help to create. The parent stellar cluster, having sculpted this immense void, now sees its legacy continue in these infant suns forming on the bubble's rim. How many of our own galaxies' star clusters began their lives on the turbulent edges of such a phenomenal structure? DEM L106 is more than a hole in space. It is a dynamic engine of cosmic renewal where destruction and creation are two sides of the same celestial coin. That sprawling stellar ecosystem, with its cycles of life and death, is all held within a strangely lopsided frame. The very backbone of the Large Magellanic Cloud, the bright bar of stars at its center, is fundamentally askew. In most barred galaxies, this central structure is a symmetrical, straight line of stars, a rigid spine running through the galactic core. But here, the bar is unmistakably off-center, warped and bent as if twisted by an immense, unseen hand. It does not align neatly with the galaxy's plane, creating a distinct and puzzling asymmetry that is visible even in telescopic images. This is not a random flaw. A warp of this magnitude is a cosmic scar, a fossil record of a violent gravitational history. The most likely culprit is a close encounter or a series of encounters with one of its celestial neighbors. The prime suspect is the small Magellanic Cloud, the LMC's smaller companion, which is locked with it in a slow, gravitational dance. As these two galaxies have swung past each other over billions of years, their mutual tidal forces, the same kind of pull that the Moon exerts on Earth's oceans, would have been strong enough to tug and distort the larger galaxy's core, pulling its central bar out of alignment. There is another, even more massive gravitational player in this drama, our own Milky Way. The immense pull of our galaxy could also be responsible for this warping, stretching the LMC's structure over cosmic time. This distorted bar is therefore more than just a collection of stars. It is a piece of forensic evidence. By studying its precise shape and orientation, astronomers can work backwards, running computer simulations to recreate the ancient interactions that must have caused it. It tells a story of a galaxy that has not evolved in serene isolation, but has been shaped, pulled, and twisted by its relationships with the cosmos around it. What other secrets of galactic evolution are written in the bent spine of this nearby island universe? That warped galactic backbone is a testament to external forces, yet some of the most profound distortions occur on the scale of a single, dying star. Deep within the cloud lies a celestial butterfly known as SMP-LMC 58, a planetary nebula whose beautiful symmetry masks a deeply violent story. This is the final glowing shroud cast off by a star in its death throes, but it is unlike any planetary nebula found in our own galaxy. Its twin lobes, stretching out in a perfect bipolar structure, are not the gentle, expanding bubbles we might expect. Instead, They are shaped by two incredibly narrow, powerful jets of gas screaming outward from the central star at speeds exceeding 600,000 kilometers per hour. These are not gentle winds, they are cosmic blowtorches, focused beams of material known as collimated outflows. Imagine trying to create a perfect, symmetrical shape by firing two high-pressure water jets into a cloud of smoke. The precision and power required are immense, and that is the puzzle at the heart of this object. Standard models of stellar death struggle to explain such focused ferocity. In a typical planetary nebula, a dying star puffs its outer layers into space in a relatively spherical, if messy, envelope, but to create these tight, fast jets, something must be focusing the star's expulsions with the power of a cosmic nozzle. The leading theory points to a hidden actor in this drama, a binary companion star too faint for us to see. As the primary star swelled into a red giant, its outer atmosphere could have spilled onto a smaller, denser companion star orbiting nearby. This transfer of mass would have swirled around the companion, forming a dense, hot accretion disk. It is this spinning disk, a natural funnel, that could then channel the outflowing material into two opposing, incredibly focused jets. The beautiful butterfly wings we see are therefore not a product of a solitary star's peaceful death. They are the scars from a gravitational struggle, the signature of a stellar partnership where one star's demise was violently sculpted by the other. How many other beautiful cosmic shapes are born from such hidden, chaotic interactions? These dark swathes of cosmic dust are far more than simple shadows. They are immense, cold complexes of gas and dust, so dense they blot out the brilliant star fields behind them, carving the galaxy's face into a pocked and porous landscape. From our vantage point, these dark nebulae create a stark, negative image of the cosmos, a silhouette of profound emptiness against the glow of millions of stars. They are the raw, unlit ingredients of future solar systems, vast molecular clouds where temperatures hover just a few degrees above absolute zero. Within these frigid, lightless realms, the initial, delicate steps of star formation are quietly taking place. Gravity works in slow motion here, gradually coaxing together particles of dust and gas into denser clumps. These are the cocoons, the stellar nurseries in their absolute infancy, long before nuclear fusion ignites and before the fierce stellar winds that clear away the surrounding cloud. Some of these dark knots may be the very seeds of future tarantula nebulas, cradling the potential for stellar explosions and runaway stars yet to come. Their darkness is not a void, it is a deep freeze, a cosmic hibernation where the building blocks of suns and planets are patiently assembling themselves in the silence. What wonders are currently taking shape, completely hidden from our view, within these light-devouring clouds? Yet these dark nurseries are not the only place where the universe conceals its true nature. Even the stars we rely on as cosmic signposts sometimes behave in baffling ways. Cepheid variable stars have long been the gold standard for measuring vast distances across space. These are pulsating giants, stars that rhythmically brighten and dim over a period of days or weeks. The key to their utility is a beautiful, straightforward relationship discovered over a century ago. The longer a Cepheid's pulsation period, the greater its true, intrinsic brightness. By comparing this known intrinsic brightness to how dim it appears from Earth, astronomers can calculate its distance with remarkable precision. It is this cosmic yardstick that first allowed us to grasp the scale of our own galaxy and the true distance to our neighboring galaxies, including the Large Magellanic Cloud itself. But within this very galaxy, our trusted rulers are showing cracks. Some of the LMC's Cepheids exhibit strange, anomalous pulsations. Their rhythms are not perfectly steady. Their periods can change subtly over time, and some show secondary pulsations that overlap the primary one. creating a complex, jittery beat in their light. This is not supposed to happen with such reliable celestial metronomes. What could cause this erratic behavior? One leading theory points to the star's internal structure. The pulsation of a Cepheid is a delicate balance, a continuous cycle of expansion and contraction driven by the complex interplay of gravity and radiation pressure deep within its atmosphere. If the internal layers of the star are not perfectly uniform, if there are zones of different composition or temperature that disrupt the smooth flow of energy, it could manifest as these strange hiccups and period shifts. It is like a perfectly tuned bell developing a tiny crack, its pure ring now tainted by an unexpected overtone. The implications of this wobble in our cosmic rulers are profound. Cepheid variables are a critical first step on the cosmic distance ladder, the very foundation upon which we measure the expansion rate of the entire universe. If our understanding of their behavior is even slightly flawed in a different galactic environment like the LMC, that small error propagates outward, affecting our measurement of how fast the cosmos is flying apart. Could the strange heartbeat of these specific stars be subtly distorting our view of the universe's ultimate fate? The anomalies in the Large Magellanic Cloud suggest that our most trusted guides still have secrets to reveal. This faint X-ray glow is not confined to any single star or nebula, but cloaks the entire galaxy in a massive, ethereal shroud. Surrounding the visible disk of the Large Magellanic Cloud is a colossal and diffuse halo of incredibly hot gas, a thin plasma burning at millions of degrees and emitting a faint whisper of X-ray radiation. This is not a solid structure you could touch, but a tenuous, sprawling atmosphere of pure energy, so vast it dwarfs the galaxy of stars it envelops. Its discovery presented an immediate puzzle. Where did this immense reservoir of superheated gas come from? The leading theories paint very different pictures of the galaxy's history. One possibility is that this halo is primordial, gas that has been falling onto the galaxy since its formation, heated to extreme temperatures as it cascaded through the galaxy's own gravitational field. It would be a fossil, a relic of the raw material from which the LMC first coalesced. Another compelling idea points to galactic theft. As the Large Magellanic Cloud orbits the vastly more massive Milky Way, the tremendous gravitational pull of our galaxy could be actively stripping gas away from its smaller companion. This stolen material, ripped from the LMC's outer regions, would be stretched into a long stream and heated by the violent process of removal, creating the very halo we detect. Yet a third explanation looks inward to the galaxy's own violent nature. The LMC has been a cauldron of star formation and supernova explosions for billions of years. Each of those stellar cataclysms, like the ones that created supernova remnants and superbubbles, has blasted trillions of tons of hot, metal-enriched gas out of the galactic disk and into the surrounding void. Over eons, this cumulative exhaust from countless stellar deaths could have slowly built up, inflating this giant, hot bubble that now surrounds the entire galaxy. This debate is more than academic. The true origin of this X-ray halo holds the key to understanding the life cycle of the galaxy itself. Is the LMC a closed system, slowly cooking in its own stellar exhaust, or is it an open system, constantly gaining and losing material in a grand, cosmic exchange with the Milky Way? The answer determines whether we are watching a galaxy in its mature, stable phase, or one that is slowly being consumed by its giant neighbor. Nestled within the cloud is a cosmic dance of two star clusters, a pairing so close and so strange it defies the usual solitude of such stellar cities. This is NGC 1850, often called the String of Pearls, a name that barely hints at its true nature. It is not one cluster, but two, locked in a mutual orbit around a common center of gravity. The primary cluster is a dense, ancient ball of stars, a classic globular cluster that has survived for billions of years. Circling it is a second, much younger cluster, a brilliant and massive collection of stars that blazed to life only recently in cosmic terms. Seeing these two together is like finding a medieval castle with a modern skyscraper orbiting it just outside its walls. Their coexistence is a profound puzzle. How can two clusters of such vastly different ages become gravitationally bound? Typically, the immense tidal forces within a galaxy tear such fragile pairs apart over time. Their survival suggests they formed together, or very nearly so, in a single colossal event. Perhaps a giant molecular cloud, unusually rich and dense, underwent two distinct, violent bursts of star formation separated by eons. The first burst created the old globular cluster. Then, millions of years later, a second wave of collapse and ignition within the same cloud gave birth to the younger, brighter cluster, the two remaining tied by their shared origin in the same pocket of space. Another, more dramatic theory involves a galactic collision, where the gravitational shockwaves of two small galaxies merging triggered these twin episodes of star birth. The very existence of this binary cluster challenges our ideas about the stability of stellar groupings and the conditions required for star formation. It presents a snapshot of a celestial partnership that should be fleeting, yet has endured, a rare and beautiful clue to the turbulent, interconnected history of star birth within the cloud. Even the most brilliant stellar giants can suddenly cloak themselves in mystery. The star known as R71 is a true titan, a luminous blue variable, one of the most massive and unstable types of stars known to exist. For decades, it shone with the light of over 1 million suns, a beacon of raw power in the Large Magellanic Cloud. Then, without warning, it began to fade. Over a period of just a few years, its brilliant light dimmed by a factor of 10, becoming a faint ghost of its former self. This was not a gentle, predictable flicker. It was a dramatic, unexpected event, as if a cosmic veil had been drawn across the star. Astronomers quickly realized what had happened. R71 had not simply cooled or collapsed. It had violently ejected a huge shell of its own material, throwing off a shroud of gas and dust that condensed around the star, forming a temporary cocoon that blocked its intense light from our view. This is the behavior of a star in extreme distress, a star so massive and so hot that it is constantly battling against its own gravity, periodically reaching a point where its outer layers can no longer hold on and are blasted into space. But the specific trigger for this particular great dimming remains a puzzle. Was it an internal convulsion, a sudden shift in the nuclear fusion processes at its core that rippled outward? Or was it the result of a hidden companion star, whose gravitational tug could have destabilized R71's already precarious atmosphere at a critical moment? The star is now slowly brightening again as the ejected cloud disperses, but the event left theorists with a profound challenge. Our models of stellar evolution struggle to predict these violent outbursts with precision. Watching R71 is like observing a sleeping volcano. We know it will erupt again, but we cannot say exactly when or how much material it will expel. Each of these eruptions brings the star closer to its ultimate fate as a titanic supernova. How many other brilliant lights in our night sky are secretly preparing for their own great dimming, their final acts foreshadowed by these self-inflicted shrouds of cosmic dust? While the galaxy's own stars forge and destroy, it is also being nourished from the outside. Vast rivers of primordial hydrogen, known as high-velocity clouds, are raining down upon the Large Magellanic Cloud from the emptiness of intergalactic space. These are not dense, glowing nebulae, but immense, diffuse structures of cold, neutral gas, moving at speeds that defy the galaxy's own rotation. They are essentially cosmic precipitation, and when these clouds collide with the galaxy's outer disk, they deliver a fresh infusion of the most fundamental star-making material. This process, called accretion, is a vital source of fuel, providing the raw hydrogen needed to forge new generations of stars. Without this external topping up, the galaxy would eventually exhaust its own gas reserves, and star formation would slowly grind to a halt. But this simple picture of cosmic nourishment is clouded by deep mysteries. Where do these high-velocity clouds truly come from? One possibility is that they are the leftover building blocks of the local group, pristine hydrogen that never fully condensed into galaxies and has been wandering the void for billions of years. Another, more dramatic theory suggests they are the torn remnants of past galactic encounters, debris ripped from the small Magellanic Cloud during its close passes with the LMC, now falling back in a long cosmic arc. Determining their origin is crucial because it dictates what kind of material the galaxy is absorbing. Is it pure, primordial hydrogen, untouched since the Big Bang? Or is it gas that has already been processed through previous generations of stars, carrying a hidden fingerprint of earlier cosmic history? The impact of this accretion is equally profound. When a massive cloud of cold gas slams into the galactic disk, it does not simply merge quietly. The collision creates immense shock waves that ripple through the interstellar medium, compressing gas and potentially triggering violent bursts of star formation. This external forcing could be the unseen hand behind some of the galaxy's most active stellar nurseries, a catalyst for creation arriving from the great dark between the galaxies. How much of the star-forming fury we see in the LMC was actually ignited by a downpour of gas from intergalactic space? This ancient stellar city holds a secret its serene appearance cannot conceal. The globular cluster NGC 1846 appears, at first glance, to be a perfect sphere of ancient suns, a relic from the earliest days of the galaxy. But a deeper look reveals a story of multiple generations, a puzzle written in starlight. Within this dense ball of hundreds of thousands of stars, astronomers have found two distinct populations of stars with vastly different ages. This is a direct challenge to a long-held cosmic rule. For decades, we believed that all globular clusters were simple, single-birth entities. The theory was straightforward. A giant cloud of primordial gas collapses in one rapid, violent burst. Every star in the cluster ignites within a relatively short cosmic window, and they all evolve together, a single-aged family of stars. But NGC 1846 breaks that rule completely. Here, nestled among the ancient, 12-billion-year-old stars, is a significant group of stars that are much younger, a mere 1 to 3 billion years old. How is this possible? How can a second generation of stars ignite billions of years after the cluster itself was born? The environment inside a globular cluster is incredibly hostile to new star formation. The first furious burst of stellar births would have blown away or heated up any remaining gas, leaving no cold, dense fuel for a second act. The presence of these younger stars means that somehow, against all odds, this cluster found a way to acquire a fresh supply of gas long after its initial formation. One compelling theory is one of cosmic cannibalism. As NGC 1846 orbited the Large Magellanic Cloud, its immense gravity may have captured and torn apart a smaller, wandering gas cloud, funneling that stolen material toward its core. In this new infusion of cold gas, compressed by the cluster's own dense gravity, a second wave of star birth was triggered. Another, even more dramatic possibility is that the cluster merged with a much younger, smaller star cluster, swallowing it whole and blending the two distinct populations into one. This would be like a retirement community suddenly acquiring a bustling new neighborhood full of young families. The implications are profound. If globular clusters are not the simple, pristine fossils we thought they were, but can experience these delayed bursts of creation, then we must reconsider their entire role in galactic evolution. They are not static museums, they are dynamic systems capable of renewing themselves through violent encounters, their histories far more complex and intertwined with the galaxy around them than we ever imagined. This invisible architecture weaves its way through the entire galaxy, a silent force shaping everything it touches. The Large Magellanic Cloud is permeated by a vast and surprisingly ordered magnetic field, a cosmic maze of invisible lines of force stretching across tens of thousands of light years. We cannot see this field directly, but we can detect its ghostly presence by studying the light from its stars. As starlight travels through space, it can become polarized, meaning its light waves vibrate in a preferred direction. This happens when the light passes through clouds of dust grains that have been systematically aligned by a magnetic field, like countless tiny compasses all pointing the same way. By mapping this polarization across the entire galaxy, astronomers have traced the field's structure, revealing a surprisingly coherent pattern that follows the galaxy's distorted bar and spiral arms. How does a galaxy with such a turbulent history, full of exploding stars and colliding gas clouds, maintain such a large-scale, organized magnetic field? The leading theory is a cosmic dynamo, a self-sustaining engine powered by the galaxy's own rotation and the churning motions of its gas. Picture it as a gigantic, slow-moving electric generator. The spinning of the galaxy twists and stretches the primordial magnetic field lines, while the turbulent energy from supernova and stellar winds amplifies them, weaving the invisible threads into the coherent web we detect today. This magnetic maze is far from a passive decoration. It exerts a profound influence on the galaxy's inner workings. The field guides the flow of tenuous gas, channeling it along invisible corridors and potentially influencing where new stars can form. It also acts as a trap and an accelerator for cosmic rays, which are subatomic particles traveling at nearly the speed of light. The magnetic field lines force these ultra-fast particles to spiral along them, confining them to the galaxy and preventing them from simply flying off into intergalactic space. This entire magnetic architecture is a fundamental yet subtle component of the galaxy's ecosystem, an unseen skeleton that helps dictate the motion of matter and the flow of energy on a truly grand scale. The hidden architecture of magnetic fields and the turbulent history of globular clusters set the stage for the quietest of cosmic revolutions. In a stellar nursery designated LH95, the standard recipe for star formation has been subtly but fundamentally rewritten. This glowing cloud of gas and dust appears, at first glance, to be a typical stellar maternity ward, similar to the Orion Nebula in our own galaxy, but when astronomers peered deep into its heart, they found a population of stars that defied all expectations. The region is teeming with an astonishing number of low-mass, faint stars, far more than any comparable nursery in the Milky Way. This is not just a minor statistical fluke. It strikes at the heart of a concept astronomers call the initial mass function, a fundamental rule that dictates how a cloud of gas partitions its material into stars of different sizes. We have long believed this rule was universal. When a giant molecular cloud collapses, it should produce a predictable distribution, a cosmic bell curve where a few massive, brilliant stars are born, a larger number of sun-like stars form, and a vast multitude of tiny, dim red dwarfs make up the majority. This ratio was thought to be a constant, a law of physics that applied everywhere, from our galactic neighborhood to the farthest reaches of the universe. LH95 shatters that assumption. Here, the balance is skewed. The nursery is overproducing these faint, lightweight stars while seemingly underproducing the stellar behemoths. What local condition could possibly alter this universal rule? The answer may lie in the unique environment of the Large Magellanic Cloud itself, its lower metallicity, that relative lack of elements heavier than hydrogen and helium, changes the way gas cools and collapses. Without as many complex molecules to radiate heat away, the cloud fragments differently as it collapses. Perhaps the gas breaks into smaller, denser clumps from the very beginning, clumps that are predisposed to become tiny stars rather than coalescing into giants. It is like trying to make a snowball with dry, powdery snow versus wet, packable snow. The starting material itself dictates the size and stability of the final product. This single, quiet nursery forces a profound question: is the initial mass function truly universal, or is it a sliding scale dependent on a galaxy's chemical history? If the recipe for star formation changes from galaxy to galaxy, then the very population of stars we see, the balance between luminous giants and dim dwarfs, is not a constant. This recalibration would ripple through all of astronomy, affecting how we estimate the mass of distant galaxies, how we model their evolution, and even how we calculate the abundance of planets. After all, every faint red dwarf is a potential sun for its own system of worlds. The quiet overachievement of LH95 suggests that the universe may have a surprising preference for building small, hiding countless faint suns in the shadows of their brilliant siblings. This stellar partnership is a time bomb with a very strange alarm clock. In a binary system catalogued as LMC 1995, a dense white dwarf star, the Earth-sized core of a dead sun, orbits dangerously close to a living star. The white dwarf's immense gravity is constantly siphoning hydrogen gas from its companion, drawing this fresh fuel onto its own scorching hot surface. This stolen material does not simply accumulate. It builds up for decades, layer upon layer, until the pressure and temperature at the base of this hydrogen ocean become unbearable. Then, in a flash of nuclear fusion, it all ignites at once. The entire surface of the white dwarf explodes in a runaway thermonuclear blast, causing the entire system to brighten by thousands of times in a matter of hours. This is a nova, a stellar flashbulb that seems to reset the clock. The explosion blasts the accumulated material into space, and the cycle of theft and buildup begins anew. What makes this system so puzzling is its timing and its fury. Most recurrent nova, as these repeating explosions are called, have predictable cycles, erupting every few decades like celestial metronomes. But the outbursts from LMC 1995 are erratic. The intervals between its explosions are inconsistent, and the brightness of each blast varies wildly, suggesting that the amount of material being stolen and the stability of the ignition process are far from steady. This is not a well-oiled machine. It is a sputtering, unpredictable engine. The violence of the outbursts themselves is also anomalous. They are unusually energetic, and the light they emit carries signatures of complex chemical elements being forged in the blasts, elements that are not normally seen in such abundance in standard nova explosions. This points to a system on the edge. The white dwarf may be teetering dangerously close to a specific mass limit, a point where a single, additional nova explosion could push it over the brink. If it crosses that threshold, the entire star would not just experience a surface flash, it would be utterly obliterated in a titanic supernova explosion, a final, cosmic detonation that would outshine entire galaxies. So each erratic flash from LMC 1995 is more than just a spectacle. It is a vital sign, a measurement of a stellar corpse slowly consuming its partner and inching toward its own ultimate destruction. Is this unpredictable flickering the final warning before a far greater cataclysm? Looming in the northern expanse of the cloud is a cavity so vast it redefines our sense of scale. This is LMC4, a supershell that spans over 6,000 light-years, a hole in the galactic fabric so immense our entire local spiral arm of the Milky Way could fit neatly inside its empty circumference. Such a structure cannot be the work of a single star. It is the cumulative echo of dozens, perhaps hundreds, of supernova explosions that have detonated over millions of years. Each stellar cataclysm delivered a powerful shockwave, and together, these concussive blasts acted like a coordinated team of cosmic bulldozers, relentlessly pushing the surrounding gas and dust outward to inflate this single, staggering void. Yet the interior of this colossal bubble is not the smooth, empty chamber one might expect. When we peer deep into this great clearing, we find it etched with intricate structures. Delicate radial spokes and subtle, concentric ripples texture the inner surface of the shell, like the complex patterns left in the sand after a retreating tide. These are not random features, they are the forensic evidence of a more complex and violent history than a simple, steady expansion. The ripples suggest that the shell has not grown smoothly. Instead, it has likely experienced distinct, powerful waves of supernova activity, a staccato rhythm of explosions where each new cluster of blasts sent a fresh shockwave rippling through the hot gas already inside the bubble, creating interference patterns that froze in place. The radial spokes, meanwhile, point like arrows back toward the shell's center, tracing the paths where particularly powerful shockwaves or the fierce stellar winds from the most massive stars punched through the expanding wall with focused intensity. This supershell is not a serene, empty space. It is a dynamic and fossilized record of stellar death on an almost unimaginable scale, its intricate inner topography telling a story of coordinated chaos, where the deaths of many stars wrote their collective history on the face of the galaxy itself. What other grand structures in the cosmos hold such detailed diaries of their own violent creation, waiting only for us to learn how to read them? The final, bloated stage of a massive star's life should be a predictable affair. These red supergiants, swollen to diameters that would engulf the orbit of Jupiter, are the prelude to a supernova, and our models of stellar evolution have long offered a clear forecast for their properties. Yet in the Large Magellanic Cloud, these aging giants are breaking the rules. They appear systematically cooler and more luminous than our best predictions allow, glowing with a deceptive and unexpected brilliance in their final years. This is not a minor accounting error. It is a fundamental flaw in our understanding of how the most massive stars behave just before their dramatic deaths. The discrepancy forces us to reconsider the very structure of these stellar behemoths. Our models typically assume a star's outer layers are relatively stable and transparent, allowing heat to radiate away efficiently. But what if the reality is far more turbulent? One compelling theory suggests that violent convection, massive bubbles of hot gas boiling up from the star's interior, could be churning the outer atmosphere into a much more extended and opaque shroud. This would be like a pot of water boiling so fiercely that a thick, steamy cloud forms above it, masking the true heat of the burner below. The extended, opaque envelope would make the star appear cooler at its visible surface while simultaneously trapping more radiation inside, causing the entire star to swell to a larger size and shine more brightly. This single anomaly has profound consequences. The brightness of a supernova is directly tied to the properties of the star that exploded. If we are misjudging the size, temperature, and structure of the progenitor red supergiants, then our interpretation of the supernova we see across the universe is also flawed. We might be miscalculating the distances to these cosmic explosions, or misidentifying the types of elements they forge and scatter into space. These stars are the calibrated candles we use to measure some of the most violent events in the cosmos, and in the Large Magellanic Cloud, they are flickering in a way we do not fully understand. Does this mean our entire timeline for the final moments of a massive star, the very countdown to its destruction, requires a fundamental rewrite? Even as we map the grand architecture of supershells and stellar anomalies, some of the most telling clues are not colossal, but fleeting. A star in the Large Magellanic Cloud will, for no apparent reason, briefly brighten over a period of weeks or months, then just as mysteriously fade back to its normal brilliance. This is not the variable pulse of a cepheid or the eruption of a nova. This is the signature of a cosmic phantom, an event known as microlensing. The cause is a phenomenon predicted by Einstein himself, the gravitational bending of light. When an invisible, compact object, anything from a rogue planet to a failed star, drifts precisely between Earth and a background star in the LMC, its gravity acts like a lens. It warps the fabric of space around it, focusing the distant star's light and causing a temporary, characteristic brightening. The star does not actually change. We are simply seeing a cosmic magnifying glass pass in front of it. The true mystery lies not in the effect, but in the nature of the lens itself. These events reveal a hidden population of dark, isolated bodies drifting in the vast halo of the galaxy. What are these invisible wanderers? Some are almost certainly rogue planets, worlds torn from their parent stars by gravitational encounters and now condemned to wander the darkness alone. Others could be brown dwarfs, objects too massive to be planets but too small to ignite as true stars, often called failed stars, but the most intriguing possibility is far more exotic. A fraction of these microlensing events may be caused by primordial black holes. These would not be the black holes formed from dying stars, but hypothetical relics from the universe's first violent moments after the Big Bang, tiny, ancient knots of density that collapsed directly into black holes. They would be nearly impossible to detect by any other means. Each microlensing event is therefore a census of the invisible. By counting these flashes and analyzing their duration and intensity, astronomers are taking a silent roll call of the dark, compact objects that make up a substantial, yet unseen, component of the galaxy's mass. How many of these phantom lenses are primordial black holes left over from the dawn of time, silently drifting through the halo of a neighboring galaxy? Every temporary brightening is a vote for a different, darker universe, one filled with ancient ghosts we are only just learning to see. The heart of a cosmic giant beats with a chaotic and unpredictable rhythm. S Doradus is not a single star, but a brilliant, unstable system, a hypergiant so vast and luminous it pushes the very limits of what a star can be. Its true nature is one of the cloud's most enduring puzzles. As evidence suggests, it may be a binary or even a triple system locked in a tight, gravitational embrace. This stellar partnership is the engine for its wild behavior. S Doradus undergoes extreme eruptions, not mere flickers but colossal outbursts where it violently expels enormous shells of its own outer layers into space. During these events, its brightness can change by a factor of 3, and its temperature plummets, making it appear as a cooler, redder giant even as it grows vastly brighter. This is not a stable aging process. It is a star in constant, violent turmoil, shedding mass at a ferocious rate. Imagine a bonfire that periodically throws off great, burning mats of its own fuel, flaring up brilliantly as it does so, only to then settle back into a different, equally unstable state. The cause of this chaos is almost certainly its complex nature. In a close binary or triple system, the gravitational tides from companion stars can violently destabilize a hypergiant's already precarious atmosphere, tugging and pulling at it until entire sections are ripped away. The transferred mass between the stars could create swirling, superheated disks that ignite sporadic, intense outbursts. We are not watching a single star die peacefully. We are witnessing a gravitational struggle, a continuous celestial battle where stars so massive they can barely hold themselves together are further torn at by their closest neighbors. What does such a violent, shared existence mean for its ultimate fate? Most stars this massive are destined to become black holes, but the extreme and continuous mass loss forced by its binarity might be stripping it down, potentially altering its final collapse into a quieter stellar corpse. S Doradus is a spectacular, real-time experiment in stellar extremes, demonstrating that the most brilliant lives in the universe are often the most turbulent and closely entwined. These invisible rivers of stars are a testament to the galaxy's slow dissolution. Stretching far beyond the visible boundaries of the Large Magellanic Cloud are vast, faint streams of stars and gas, cosmic debris being steadily stripped away by the immense gravitational pull of our own Milky Way. These are tidal streams, the direct evidence of an ongoing galactic disruption that has been unfolding for billions of years. As the LMC travels through the halo of our far larger galaxy, it is not moving through empty space. It is swimming through the Milky Way's own powerful gravitational field, and this creates a tidal force, much like the Moon's pull on Earth's oceans. The side of the LMC closest to the Milky Way feels a stronger pull than the side farther away, and this difference stretches the entire galaxy, pulling it apart. This relentless cosmic tug-of-war is slowly shredding the smaller galaxy, drawing out long, tenuous tails of material that trace its orbital path like breadcrumbs left in the dark. These streams are more than just a sign of current destruction. They are a fossil record of past interactions and a precise clock for a future cataclysm. By mapping the exact paths and densities of these stellar rivers, astronomers can rewind the cosmic tape, calculating the precise orbits of both galaxies and determining how many close passes they have made. The data is unequivocal. The Milky Way and the Large Magellanic Cloud are not just distant neighbors, they are a bound pair, and their gravitational dance is a prelude to a final act. The same tidal forces that are now pulling streams of stars from the LMC are also gradually sapping its orbital energy. With each passing orbit, the cloud is drifting closer to the colossal gravity well at the center of our galaxy. This slow, cosmic spiral means that in approximately 2.5 billion years, the Large Magellanic Cloud will merge with the Milky Way. It will not be a collision of stars, for the spaces between them are far too vast. Instead, it will be a monumental blending of structures, a gravitational upheaval that will violently warp the spiral arms of our galaxy and funnel vast waves of gas toward the central supermassive black hole, potentially igniting it into a brilliant quasar. The faint, ghostly streams we see today are the first gentle threads of this future cosmic tapestry, a slow-motion preview of the incredible transformation that awaits our home galaxy. But even the faint glow of distant suns can be misleading. Deep within the cloud's dusty lanes, astronomers have pinpointed strange, brilliant beacons that burn only in the infrared. These are the unidentified infrared objects, point-like sources of intense heat radiation that seem to have no true face. When you point an optical telescope at their coordinates, you often find only an empty patch of darkness. Yet in the infrared spectrum, they blaze with the power of a hidden furnace. This intense glow is the unmistakable signature of an object that is deeply enshrouded, wrapped in a thick, opaque cocoon of cosmic dust. One of the most compelling explanations is that we are witnessing the very first stages of star formation, a process so young and violent it must hide from view. These could be protostars, stellar embryos still in the act of collapsing from a cloud of gas. As gravity pulls the material inward, the core heats up, but the infouling dust and gas are so dense they absorb the visible light and re-radiate it as infrared, hiding the newborn star from our direct sight. It is a cosmic birth happening behind a thick, warm curtain, But there is another, far more exotic possibility. Some of these mysterious infrared sources might not be infant stars at all, but rather stellar hybrids of a truly bizarre nature known as Thorn-Zit-Cow objects. Picture a red supergiant star, but one with a terrifying secret hidden in its core. Instead of a furnace of nuclear fusion, the heart of this giant contains a neutron star. The theory suggests that in a close binary dance, a neutron star could have spiraled into its massive companion, plunging through the outer layers to become a captive core within the larger star. This would create a stellar Russian nesting doll, a bloated, cool giant powered not by its own fusion in the center, but by the incredible heat radiating from the embedded neutron star's surface. The outer envelope of the giant would be so thick and turbulent that it would smother the high-energy radiation, allowing only a deep, red infrared glow to escape. How would we ever distinguish a Thorn-Zit-Cow object from a simple, dust-enshrouded young star? The answer may lie in the chemical fingerprints within their light. The unique nuclear processes occurring around a neutron star core are predicted to produce an overabundance of very specific, heavy elements like lithium, rubidium, and molybdenum. Finding those exotic signatures in the infrared glow would be the smoking gun, evidence of a star that has swallowed the corpse of its dead companion and is now living on borrowed time. These unidentified objects represent a fundamental choice in our understanding of stellar life. Are we looking at the earliest moments of a star's life, hidden in its natal cocoon, or are we seeing one of the strangest possible ends, a star whose heart has been replaced by a dense, dead relic? The infrared sky holds both possibilities, leaving us to wonder what truly lies within those warm, dark shrouds. This galactic wobble is not a gentle, unified spin. The entire disk of the Large Magellanic Cloud, the flat plane containing most of its stars and gas, is moving in a strange and unsettled way. Instead of a smooth, orderly rotation like a spinning vinyl record, its motions are chaotic and twisted. Stars and gas clouds on one side of the galaxy are not moving in perfect sync with those on the other. The disk appears warped, with sections rising above and dipping below the main plane, creating a shape more like a bent hat brim than a perfect circle. This peculiar kinematics, the study of motion, reveals a galaxy that has been profoundly disturbed. A calm, isolated disk would settle into a stable, predictable rotation over billions of years. The twisted motions we see are the lingering tremors from past violence. The prime suspects are the same gravitational forces that warped the central bar. The relentless tidal tugs from both the small Magellanic Cloud and the colossal Milky Way have not just pulled on the galaxy's spine, they have sent shockwaves through the entire disk, setting off a slow motion wobble that persists to this day. It is like watching the ripples in a pond long after a stone has been thrown in, but the disturbances are not only external, internal dynamics play a role as well. The massive energy released from countless supernova and stellar winds within the galaxy does not just create superbubbles. These explosions punch upwards, heating the gas in the disk and pushing it around, adding random, turbulent motions to the large-scale gravitational twisting. The galaxy is not a rigid structure. It is a fluid, dynamic entity, its motions a complex tapestry woven from the threads of external harassment and internal fury. How long will it take for these chaotic motions to finally settle? The answer may be never, as the galaxy continues its long spiral toward its eventual merger, a journey that guarantees new gravitational shocks will continue to rattle its already unsteady frame. This absence of stellar titans presents a cosmic paradox. The Large Magellanic Cloud is a ferocious star-forming engine, a galaxy that should, by all rights, be building the most colossal star clusters in the local universe. Yet when we search for true superstar clusters, the dense, massive cities of stars that contain the mass of millions of suns crammed into a region just a few dozen light years across, we find a puzzling void. Other galaxies with similar levels of star-forming fury are studded with these brilliant, compact metropolises. Why does the LMC, for all its stellar productivity, seem incapable of forging them? The answer appears to lie not in the present chaos, but in the galaxy's quiet past and its fundamental composition. Creating a superstar cluster is not just about having a lot of gas. It requires a specific, extreme set of conditions, a single, giant molecular cloud of incredible density and stability, one that can collapse in a single, coordinated, and rapid burst of star formation without being torn apart by internal or external pressures. The turbulent, metal-poor environment of the Large Magellanic Cloud may simply be too chaotic to allow such a pristine, monstrous cloud to form and survive long enough to complete the process. Its interstellar medium is more prone to fragmenting into many smaller clusters rather than condensing into one overwhelming giant. It is the difference between a quiet, deep lake freezing into a single, solid sheet of ice and a choppy, wind-blown sea freezing into a million separate, jostling chunks. The missing superstar clusters are a silent testament to a galactic environment that is just a little too wild, a little too primordial to cross that specific threshold of cosmic construction. This absence forces us to ask a deeper question about the universe's grand designs. Are the most magnificent stellar cities reserved only for galaxies that started with a richer, more stable set of building blocks? Even the galaxy's own weight is a subject of fierce debate, a hidden controversy surrounding its most mysterious component, the true mass of the Large Magellanic Cloud, and specifically the amount of invisible dark matter holding it together, is one of the most contentious puzzles in modern cosmology. On one side of the argument, measurements of the galaxy's rotation curve suggest a massive, extended halo of dark matter. Astronomers chart the orbital speeds of stars and gas clouds at different distances from the galactic center. In a system dominated by visible matter, stars on the outer edges should orbit more slowly, like planets in our solar system, but that is not what we see. The outer stars of the LMC are whipping around just as fast as the inner ones, a clear indicator that they are embedded within a huge, unseen sphere of gravitational influence, a dark matter halo. This interpretation paints the LMC as a relatively hefty dwarf galaxy, firmly anchored by its own substantial dark matter, yet other methods of weighing the galaxy tell a completely different story. By studying the motions of a small, orbiting satellite galaxies and the delicate, stretching tidal streams being pulled from the LMC by the Milky Way, some researchers calculate a much lower mass. These gravitational fingerprints seem to imply that the cloud is surprisingly lightweight for its size, possessing far less dark matter than the rotation curve suggests. How can these two sets of evidence be so wildly contradictory? The implications are profound, touching on the very nature of dark matter itself. If the rotation curve is correct, then our understanding of how tidal forces strip mass from small galaxies may be flawed. But if the tidal stream measurements are right, it challenges our most fundamental models of how galaxies form and hold themselves together. It forces us to ask a startling question. Could the properties of dark matter be different here than we have assumed? Perhaps dark matter particles can interact with each other in ways we have not anticipated, creating a halo that is smoother or more condensed than our theories allow. This single galactic weight check has become a critical test for our entire cosmological framework, proving that even the ghostly, invisible stuff of the universe can hold stunning surprises when examined up close. From runaway stars to phantom stellar corpses, The 30 wonders we have explored reveal a galaxy fundamentally unlike our own. The Large Magellanic Cloud is not a placid collection of stars. It is a cosmic laboratory of extremes, a place where stars form with ferocious inefficiency, die leaving invisible hearts, and warp the fabric of space itself. Each phenomenon, from the chemical imbalance of its carbon stars to the chaotic wobble of its entire disk, provides a critical test for our understanding of physics. This neighboring galaxy forces us to question the universality of stellar life cycles, the true nature of dark matter, and the very rules that govern how galaxies live and die. Its proximity offers us a front-row seat to cosmic processes that shape the entire universe, yet its strangeness reminds us how much we still have to learn. The endless mysteries locked within this ghostly cloud of light are a profound reminder that the universe is far richer and more bizarre than we ever anticipated. So, as we look up at that faint smudge in the southern sky, which of its secrets captured your imagination the most? Was it the phantom heart of supernova 1987A, the chaotic dance of S. Doradus, or the silent, dark matter controversy that could reshape cosmology